Alright, the first part, I'll skip it because we did it earlier today. That's again explain what EMF is. So we did that one already. Part 2. Why do you think batteries with a large current have a low internal resistance? So if you have a battery here, why do you think the R will be small if the I is really big? Well, what happens with batteries? They get warm, don't they? And how much heat energy would be coming off of this resistor? Do you remember the formula for the heat energy? It'd be I squared or T. Okay? So if the I is really big, then the Q will be really big. So the only way you could help to try and make it smaller is if the resistor is smaller. So in other words, you minimize the energy lost through heat. Okay? So less energy is lost via heat in the small resistor. Less energy is lost via. Are you talking about this one here?
Explain.
You know via. Do you know via? Like true, yeah.
But
It says it on the bus. You know, when you look at where it's going, it would say Tala via city centre. Yeah? You know this? Oh, good. Okay, part 3 now. If you have, like in a school, a high voltage, why would you like a big resistor? Now, I think they're trying to help you by saying it's in a school. So if you're in a school lab, why would you have a high voltage and a big resistor?
Many students.
Now don't guess, think.
it's different.
Why would you like the resistance to be big in a school lab battery if the voltage is big? So in other words, you know that this is a big number here. Why would you also like the resistor to be big as well?
Less dangerous.
Yeah, but like, why is it less
Because
dangerous?
if, like if the V is big and the R is big, the I is gonna be small.
Yes.
So
Well, it's kind of really the opposite of the last point. That you don't want much power coming out, right? Yeah, no, I get what you're saying. Can we try and give it maybe as a formula? So what forms do we have? We have V equals I or. Yes. Power is P equals IV. Now we don't know I, but we have the formula V equals I or. So what would I equal? V over or.
V squared.
So times V, so we get V squared over R. So in other words, if the voltage is big, the power will be big as well. But if you have a big resistor, then you'll make the power smaller. So in other words, it makes it safer because it will have less power. So it's safer because it will have less power. So in total, there's 4 marks for everything so far.
Wow.
Mm-hmm. Can I go down now? Yep. Okay. Did you say no? Yes.
No, please. Wait, what?
What?
No, please.
No, please. Like,
He said
no, but please.
no. He said no. Yes, please.
Oh.
Okay, now you can.
Okay. Yes.
Okay, doesn't mean anything.
Does it make sense?
Go on.
Do you want to stop or continue? Yes.
I would like to stop or continue. One of the two, please. Okay, in the circuit shown below, the battery has EMF and resistance. Okay. So I'll draw this circuit for you. You got this one here. And there's a battery here. There's another battery here. But I'm not, I think they're being a little unclear. I think they're saying it's E for both batteries. So I'm just going to draw one battery, okay? And then you have a small resistor. And then here there is one resistor. We call it resistor A. And then another resistor here. We call it resistor B. And there's actually a little switch here. And there's something here that will tell you the current, and then you can also measure the voltage. So there's a voltmeter, different color. There's a voltmeter attached along the terminals here again. So that's the circuit. So please draw that first. Got that? Give me.
To make it sure you cannot help it.
Oh, sure, just pass it around.
Continue.
Let everyone do it. It's fine.
To explode.
Pass it to Avenue, he will. I know he would.
Douche.
Curly?
Open it.
No, I just.
No. We did not open it.
Alright,
Open it.
pass it back. Say by the time we finish it probably will be safe, okay?
No.
If it isn't, I'm going to make it like as if it's a champagne bottle. Everywhere. Like just one NASCAR or something like that.
Yes. Okay. Now, when the switch is open, so do you have to? I'll wait for you to draw that first, okay? Because I'll need to make changes. Did you draw that, Curdy?
Yeah.
Yes. Okay.
Why?
Because there's two situations when the switch is open and closed. So firstly, they deal with it when it's open. No?
No.
It's down the bottom there.
So by open you mean like not on.
Yeah, like how it is in the diagram here.
So then that means the bottom part should.
No, I was thinking.
Well, it will be for the second half.
second
Yeah. It's like it's not there. Yeah.
So let's open it to the first floor.
Yeah, so can I look at it now? So firstly the switch is open. So which way does the current go? It'll go this way. It'll go across, down here, across here, and so on, all the way back to the start here. And your voltage is from here all the way around to here. So in fact, your voltage tells you the voltage where? Really between, through the resistor, yeah? Now they give you some information. They say the reading on the voltmeter is 16.2. Yeah, the current is 1.2, and then the reading on the voltmeter is 16.2. And the first question, kind of easy peasy, what's the resistance here? So what formula do we have there? Yeah, V equals IR. So we get R equals V over I. So that'd be 16.2 over 1.2. So that's for 2 marks, which is good. Oh, you have it. What is it? 13.5. Okay. Good. Okay, 2 marks. Write down an equation for the E. So let's pretend now, he doesn't ask you to solve it, he just wants an equation. So what equation or what rule do you use now?
Correct.
Which one? Kirchhoff. Which rule? The loop rule. So starting here, E minus the voltage here, which is IR, but we kind of know the voltage already. What was it? 16.2. And then go all the way back to here, minus I or equals 0. So he says then write an equation to calculate the EMF in terms of the internal resistance. So he does not want the I here. But actually, sorry, we do know the I. What was it? So that should be here 1.2. There we go. So he would like that. Yeah, there you go. So that's another 2 marks for that. Is that okay? Yes? Now, next part. So that was part B. So now on to part C. Can I remove this so I don't have to draw it again?
Yeah.
Yes, do you have it? You have this information here still, yes? Okay. Yes?
No.
Now, the next part of the question is, they say the switch is closed now. So now the current goes both directions here. So this is I1, and then here will be, for example, I2, I3, and then here still I2, I3, and then back here will be I1. Yeah. Okay. Now it says the reading on the voltmeter is 15 volts and the current is now 2 amps on the voltmeter and the ammeter. But the first question is, explain why does the voltage drop? So we've seen this before. When you close the switch, why does the voltage drop? Yeah, because the resistance increased. So I don't even think I'll write that down. What's wrong?
When we close the switch,
Yes.
the total resistance decrease. Resistance increase.
Again, when we close the switch.
When you close the switch, the voltage
Goes
drops.
down,
So when the resistance, because those two resistors are in parallel.
Yeah, so they will be like the resistance, the total resistance after you close the switch.
But we don't know the value of the other resistor. Okay, if it was really big or really small, it would change the answer.
It has to be lower, like the total resistance has to be lower than the smallest one of them.
Tell you what, I'll check the answer in a minute, okay? But I feel like even if it is right or wrong, they often would want you to say something like this. But you're saying that if I close the switch, the voltage drops. Oh, okay, sorry, I think I misread it. When I close the switch, the voltage drops. If the voltage drops, that means it's a smaller number. The reason it's a smaller number is because there will be, as you said, less resistance now. Because when you connect resistors in parallel, that's less than if they're in series. So yeah, the voltage, it's use of English here is my problem. Voltage drops. What they mean is the reading on the voltmeter dropped. I'll say it, okay? Picture this number here. When you close the switch, this number gets smaller. If this number is smaller, it means there's less voltage used up from going from here all the way back to here. If there's less voltage used up, it means it's because there was less resistance. Why would there be less resistance? Because when you put two resistors in parallel, you actually make the total resistance smaller. But if you put them in series, you make it bigger. Do I need to write that down or is
Oh,
it's okay? Alright. I'm sorry. I got mostly it's fine here. Do you need me to say it again or to write it down?
Yeah, same.
Alright. No, actually, you say it back to me and I'll tell you if you heard it right or wrong.
Okay, when you close the switch,
Yep.
it will be in invertible. So
Say that again. It'd be what?
it will be like this.
Yeah, you close the switch.
Yes.
Good. And then what happens?
The resistance
Yes.
will be
In parallel.
yes.
Yes, go on.
So it will be small.
Yes. And if the resistance is smaller, what does that mean about the voltage? Do you use more or less?
Plus.
Yes. Good, so you did get it. Good man. Alright, leave him alone.
Bravo.
At least he's coming to school.
Okay.
So you be nice to him,
I
okay?
applauded. It wasn't
Yes.
sarcastic applause. It wasn't slow clap.
Now, write a new equation. So now we need to write another equation. So we'll use, again, we could use the loop rule, we could use the junction rule, but I think because they want E in the equation, we need to use the loop rule. So should we go on the inner loop or the outer loop now? What do you think? Which one would be a little bit better? I think the inner one, because we have the value of the resistance on the inside one. So we get here, I'll write up the top, E minus I2. And what was the OR we got previously, or did we get it? We did get it.
No, we got I only.
Oh, we didn't get the OR? Okay. Are you sure?
No, we have 13.5 for I.
Oh yeah, R is 13.5.
13.5. And then at the last bit here, minus I1 OR equal 0. Now, I have that equation gone now, but the one I gave you earlier, can you read it back to me when the switch was closed? Sorry, when the switch was open. What was the one you got a moment ago?
E minus 16.2 minus 1.2 R.
E minus 16.2.
2 R. Yeah, minus 1.2 R.
Minus 1.2,
R.
like this was it here, yeah?
Yes.
Equal
0.
0. Okay. Alright. And yeah. We want to solve these equations now. But the only thing is we don't know the I2. So we need to do something with the I2. So now I think I need to use another loop rule. So let me just forget about that for the moment. Oh look, we have some here we didn't use. So we know that the I is I1, because it's going through this one, is 2. So I can go, I don't have an I1 here, do I? Oh, here it is. Good. So we know that's 2. So let's replace that. 2. Now we also know that the voltage is 15. The voltage is 15. You got that? But that voltage does not include these two pieces here because it's from here to the end. Yes? Yes? Okay, I'm not sure if I'm getting or understanding, yes? Okay, so if I look at these two equations, how many unknowns do I have in them?
2.
I have 3 actually, unfortunately. The E, the O, and the I2. So I need to do something about the I2. So do we know what the RB, the other resistor is? No. No, I don't. I think I have to write now another law down. So what law have I not used yet? I haven't used the junction law. So let's take this one here. What's going into this junction? I1, which is 2. And then what's coming out of the junction? I2 and I3. So how many unknowns do I have now?
Yeah.
4. So then I need another equation. So I feel like this isn't the right way to be going. But I haven't used this 15 yet. Oh, I know. So here we go. Remember Kirchhoff's says that the voltage when you go around any loop will have to be 0. Okay? So in other words, if I start here and go all the way around, it's 15. So in fact, these two pieces together here, they must also be 15. If you look up here. Let's say I start here, and I go all the way around. Back here, the total should be 0. So in here, whatever it is, when I minus everything going along, I'm minusing 15. Please, Avenue, look up. I'll say this again.
Please.
I start here. I don't know what this voltage is in here, but I know when I go all the way around, I have to minus, 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 and at the back, I should get 0. But he tells me here that it's 15 volts, meaning that from here all the way back to here is 15. Okay? So that means the total here should be 15. Now just be careful. Does this one add or subtract to the total voltage? Subtract. So in other words, E minus I1 OR should equal 15. So E minus I1 OR should equal 15. And do I have I1? I do. I1 was 2. There we go. Okay. Okay, so now we can get the OR, the E, and the I2. Yeah, sorry. Just to save time, because we've done 2 examples like this, if you have those equations written down, we'll just type them into Derive to get the answers, okay? So did you have them written down? Brandon, are you making notes? Good, good. Just checking.
Sorry, how to get...
No, go on. How to get which one?
How did you get 15?
How did I get number 1 here?
Yeah.
We will after this one. Sayun, if you look up. Maybe if I go here to the side. So, oops. Okay. Okay, so if I start here and I go all the way around, I know the total should be 0. If I put a voltmeter here and here, I know, for example, going this way, the total will be 15 because it says it on the voltmeter. So that means if I think about it as starting here, I'd have this one minus 15.
But you didn't say 15.
It did say 15. It did. It was given in the question 15. Then minus I or here, that should equal 0. So then I get, and this was 2. So then I get E minus 2R equals 15, which is what I have there. So that 15, where is it? That's given in the question.
Yeah,
it says,
it's 15 volts.
it
And
reads
2 amps.
15 volts on that.
And it's 2 amps here.
Yeah. Okay, can you read these questions out to me into Derive, please? So, what's the first one?
E minus 2R equals 15.
E minus 2R equals
15.
15. Second one?
E minus 16.2
Yeah.
minus 1.2R
Yes.
equals 0.
Yes.
E minus I2.
Which I'll just call it X.
Yeah, and then square bracket 13.5.
And then bracket 13.5.
Minus 2R equals 0.
Okay, solve system trail. Good. So he would like to know what is the OR and what is the E. So the OR is 1.5 and the E is 18 volts. So when you solve your equations, there they are there. You get OR is 1.5 and then the E, what did I just say? It was 18? No, the answer. There it is, 18 and 1.5. 18 volts, yeah. So, just to recap, this one here and this one here, they were Kirchhoff's. So was this one here, but the 15 came from the voltmeter. Okay. Which law did I use? In fact, I only used Kirchhoff's first law, loop law here. There's a last part to this now, and they want you to calculate the resistance in the RB here. Now, what is the total voltage that's going through RA and RB? I think we can do this using Ohm's law. What's the total voltage going through RA and RB? We know it because it says it here. What is it? 15. So V equals I. Now what's the total current? Yeah, which is how much here? 2. So I know the total resistance should equal 7.5. Now what is the formula when you have two resistors in parallel? 1 over 7.5 equals 1 over RA. Now I think we know RA, don't we? What was the 13.5? Okay, so if we just type that in, we can get the RB.
16.875. I'm not sure about that.
It sounds good. It sounds believable. You know, if you said the answer was 605, I'd be like, oh. No. If you said the answer was minus 605, then we'd have a problem. Yeah. Minus square root minus 1. Oh dear. Over 0.
Wait.
Yeah, just before we take the break now. Wait.
Oh.
See, it's just like last time. Sorry. Just before we take the break. I've done 3 of these questions now. So when you come back, probably get another 3 done, which isn't too bad because there's 8 in total. So this revision will only be good for you if you're practicing these questions at home too.
I'm listening. I get it. Yes.
This book I'm using is on Moodle. I just updated it again today. All right, take your break time now.